Good morning, gentlemen. Today is Tuesday, March the 24th, and today we'll be talking about section 10.3, which is all about kinetic energy. Uh, so, the obviously we talked about kinetic energy the other day. We said that it was um, the energy of motion, and so when an object is in motion, we have two things that we need to take into account with it. Those two things are, of course, the mass of the object as well as the velocity. So, uh, kinetic energy is the energy of motion. Okay, if you look at the formula in the top box there, K equals 1/2 mv squared. So it's the kinetic energy of an object of mass m moving with a speed v. The other thing that I do want you to realize is that if you look carefully, the formula for momentum, linear momentum, is right here in the formula, m times v. All right, this is one of the things that Newton's calculus allows us to do, to relate kinetic energy and momentum, because the momentum formula is the integral of the kinetic energy formula, and the kinetic energy formula is the derivative of the momentum formula. Now, kinetic energy can exist in two different forms: translational, for the motion of an object moving along a straight line path, and rotational for the movement of an object around an axis. And if you look carefully at the yellow box down here, all right, notice that this formula is the formula for rotational momentum. All right, the moment of inertia times omega, which is the rotational velocity or angular velocity here. All right, so 1/2 I times omega squared. Now, in terms of rotational kinetic energy, we can do a couple of things. All right, it is simply a way of expressing the sum of all the kinetic energy of every single part of a moving or rotating object. And so, in order to calculate the rotational kinetic energy, instead of using the mass, you use the inertia, and instead of using linear velocity, you use the angular velocity. But each particle in, for example, the fan blade that you see here, the blades that you see here, the linear velocity is v1, which is equal to the rotational velocity times the r1, the distance here. And the linear velocity v2 of particle m2 here is equal to v2 times the rotational velocity times r2. Notice again that the rotational velocity is the same for all points on each of the three blades that you see here. So let's go to example 10.5, the speed of a bobsled after pushing. So we've got a two-man bobsled with a mass of 390 kilograms. Starting from rest, the two racers push the sled for the first 50 meters with a net force of 270 newtons. Neglecting friction, what is the sled's speed at the end of the 50 meters? All right, so we begin, as we always do, by making ourselves a laundry list and drawing ourselves a picture. Let me move my ugly mug out of here for a minute. Excuse me. Now, we're going to assume that friction is negligible, so that there's no friction force that we have to work against here. So there's no change in the sled's thermal energy. No heat is being generated here. Now, that's not really realistic, but we'll assume in this case that it's true. Because the sled's height is constant, its gravitational potential energy is unchanged. Therefore, the work energy equation is simply the change in kinetic energy is going to equal the amount of work that we do here. So therefore, we can find the sled's final kinetic energy and therefore solve for its speed by finding the amount of work done by the racers as they push on the sled. So we make ourselves a laundry list down here. Okay, we've got mass, we've got displacement, we've got force, and we know that the initial velocity is 0 meters per second. and we're asked to find the final velocity. So what we're going to do here is use this formula, delta K equals W, and replace delta K with 1/2 mvf squared, right? Because the VO squared term is 0. And set that equal to force times displacement. And if you look carefully, we've got all the variables that we need in our laundry list, with the exception, of course, of VF. So if we use the work energy equation, we've got the delta K is equal to the final kinetic energy minus the initial kinetic energy, and we set that equal to work. Rearranging to solve for final kinetic energy, we have initial kinetic energy plus work. But again, because the initial velocity is 0, this term goes away. And so we're left with 1/2 mv squared equals force times displacement. We rearrange it algebraically, and we get VF equals, dang it, the square root of 2 times F times D all over M. And if we plug and chug from this point, we get 8.3 meters per second as our answer. Okay. So that brings us to the end of this lesson. Your homework for today is questions 7 through 15 on the kinetic energy homework at the end of chapter 10. And I will talk to you tomorrow. Have yourselves a lovely and blessed Tuesday.